Good morning to everyone. It's morning here in the Netherlands right now. I have already shared my screen, I think, so I will put my slides up. And let's go into presentation mode. So I hope that's the slides, Tom.
Apologies, Narendra. I cannot seem to be. Oh, perhaps there's some issue on my end. Apologies. Yeah, please continue.
Okay, so we have the slides on there now. Okay. Uh, so I'm assuming we have the slides up there, and I will begin. So I will talk to you today about how we can build interpretable and realistic generative models using likelihood-free Bayesian inference. So there is a lot to unpack in this title. What's likelihood-free Bayesian inference, and what sort of interpretable and realistic generative models are we talking about? We will go through that in the talk. Um, but before beginning with the serious stuff, a little bit about myself. I am a research scientist at Philips Research in Eindhoven in the Netherlands, and have worked in a variety of data science domains, which range from sort and recommendations and NLP to marketing budget optimization. Previously, before I was working at Philips, I did my PhD um, in neuroscience from Brandeis University. And I also worked as an ML scientist at TripAdvisor for a couple of years. And at this time, I was living in Boston in the US, where I lived for about a decade. I am a longtime Bayesian, and my foray into Bayesian inference began during my PhD and has continued into my industry work as well. I also love cycling, which is a love that started while I was living in Boston, and now living in the Netherlands. I'm learning more about bicycles and sustainable transport. And feel free to visit my website to learn more about me. Um, this this talk is based on a research project which I'll be running through as an example, which is a very collaborative research project with all these people. So we have Amin Rahimian, who is an assistant professor at the University of Pittsburgh, uh, Shrabasti Banerjee, who is an assistant professor in Tilburg University here in the Netherlands, and Diego Sanchez Perez, who is our research assistant through the Tilburg Science Hub, also in Tilburg University. Um, so with that, to begin, I want to present to you the idea that we can think about two different kinds of machine learning models. And models can be discriminative or they can be generative. So what I mean by that is discriminative models are those that can differentiate between different classes of targets. So they can, based on the inputs, they can produce targets of different kinds. Whereas generative models are those that can generate the data points that look like the inputs themselves. So if you give the model a text like cat, it will produce cat images or dog images, for instance here. So these are two very different kinds of models. And the dilemma that I want to put in the center in this talk is that discriminative machine learning models can be brittle. And I'm sure a lot of people in this audience are familiar with things like adversarial attacks, where you can have a model that predicts this picture to be the picture of a pig with high confidence, but then if you add a small amount of a specific kind of noise to this input, the same model with high probability predicts this to be the picture of an airliner, for instance. So discriminative models sometimes can provide predictions and probabilities that tend to be unreliable. Um, there is a lot of research in this domain and a lot of the different hypotheses of why this might be happening. But there is one specific hypothesis that I want to focus on, which is that discriminative machine learning models are brittle because they do not model the distribution of the inputs. They do not model P of X. So to understand that, what discriminative models do is that they model the conditional probability of targets given inputs. So they model P of Y given X. Um, but, uh, but on the other hand, if we look at generative models, they just don't model P of Y given X, they model P of Y and X. That would mean they model P of Y given X as well as P of X. And how this helps is if they are faced with unfamiliar inputs, which we can call out of domain inputs, that the model has not seen in the training data, then discriminative models predict with this P of y given XOD, and that leads to unreliable predictions, or unreliable probabilities or confidence with the predictions. Whereas generative models do know that P of X OOD itself is small, because that data is not something they have seen previously, and so the P of Y given X OOD will also be small. So they are able to sort of put probability estimates on things that they don't know about, and they can be robust in that manner. So with that line of thinking, there has been a lot of research in machine learning in the field of generative modeling, which has led to us living in the age of really great and deep generative models. So we can have models like DALI, which I'm sure many of you are familiar with, which can produce images based on a text input. So maybe the input here was avocado chair, and then DALI produces all of these images, which are very realistic looking and correspond to the text input that has been provided. And there are text generation models as well, like GPT, BERT, and all their descendants. So these models are amazing. There's been a lot of great research in this domain, and they produce really realistic looking inputs. But one of the issues that continues is that these models do not really get us to robust and interpretable machine learning models, and that's the case because of two different reasons. The first one being that it is not clear for these generative models what are the parameters or features that they are using to generate the data. So we don't have really an insight into the data generative process, and it's not clear how the data is being generated in the first place. So what would be a much better situation to have would be a generative model where we can directly specify parameters of consequence. We could think of these as hypothesized causal factors. We can think about, as scientists, we can think about the process we are studying, and we can hypothesize factors that matter, and if we can build a generative model out of that, that would be great. That's what we want to do. In addition, one thing that is hard with many of the generative models that we have today is that it's not very clear how we can use the generated data in downstream discriminative task, any sort of the downstream task, and that's because it's hard to calculate for many of these models this p of the probability of any test input that we provide to the model, because that from a Bayesian perspective, that would be an integration over the parameters of the model over the posterior that we have over the parameters. And since the parameters themselves are not really interpretable, this is a hard thing to do. It's not clear how we would do this. So if we had a generative model where we can specify the parameters of consequence, and in addition, if we could do Bayesian posterior inference uh, over the parameters of that generative model, that would be a great situation for us, and that can get us some way towards the robust and interpretable machine learning models and systems. And today I want to argue to you that a really common and really old way of modeling, which is common across many science and engineering fields, might be a possible answer to this dilemma. And these models are and the models that I want to talk to you about are simulation based generative models. So these models we could have models, for instance, of an aircraft in a wind tunnel, where we can specify things like the aircraft's wingspan and so on. We could have neural circuit simulations. We could have universe simulations, for instance, and I'm sure most of you have seen examples of such models in any scientific field that you have studied. And it's also related to the relatively newer concept of digital twin. Um, but it's not very common to use these models in a machine learning setting. And in this talk today, I want to make an effort to do that and show you an example of how we applied these ideas in a specific use case that we are interested in. So to to jump into that, we as industry professionals and social science researchers, so my collaborators are social science researchers, we are interested in why and how users leave ratings on online platforms. So I don't have to convince anyone in this crowd, I'm sure, that online reviews and ratings are crucial in e-commerce. And we consult ratings on websites like Amazon and websites like TripAdvisor and so many other websites. And what we wanted to do as researchers is to design a generative model of how users leave online ratings, and we wanted to do this ground up using consequential parameters like the costs to leaving a rating, or the herding of users' opinions of products. So how is a user's opinion of a product affected by other users' opinions about the same product? So we wanted to use these parameters and build a generative model, and that we did using a generative simulation model. So what we built is called an agent-based generative simulation of ratings on an online marketplace. And agent-based simulations are super common in the social sciences, so this is not a new idea at all. But we built a specific one for our use case here. So what we have here is an agent. You can think of it as a user who comes on the marketplace, which has a lot of products, and using some sort of a user product similarity measure, which we do by calculating user and product embeddings using star space, which is a tool I would encourage you to look into if you are interested in that domain. So the user uses this similarity measure to consider a set of products that they might buy today. So maybe today they are interested in electronics, and these are the products they have in their consideration set. Then they calculate a score over the products in the consideration set, which is a mixture of the similarity that the user has towards each of the products, sort of how much are they interested in each of these products, plus the average rating of the product, which is a reflection of the quality of the product. And using that score, the user calculates a choice probability based on which the user selects one product, the headphone in this case, that they choose to buy. So assume that this user came in and bought a headphone on this marketplace. Once this decision to purchase is done, the user goes on to decide whether or not to rate the product. And this is how that happens. The user looks at the existing ratings of the product, and based on that, the user forms an expectation about the quality of the product and buys the product. And then they listen to music from the headphone, and they have a real experience. They actually experience the product, and that can lead to a discrepancy. There can be a discrepancy between what they had expected based on the ratings that they saw before buying the product, and their actual real experience. And based on this discrepancy, they make the decision of leaving a rating or not. So if the discrepancy is small, if their reality and their expectation are well matched, then they decide not to leave a rating. They think that it maybe is not worth the effort to post a rating. But if they have a really good experience, much better than expected, they might leave a 5-star rating. If they have a really bad experience, they might leave a 1-star rating. And we make these decisions in our models using these parameters, which we call cost parameters, rho plus and rho minus, which basically control the extent to which which basically control how large this discrepancy has to be for the user to leave a rating and what sort of rating they will leave. So as you can see, these are parameters that are of consequence in the actual the decision making process of the user. Eventually, in the model that we actually built, there are 8 model parameters per simulated product. So there are the cost parameters that I talked to you about already. There is a propensity of herding, which is to what extent is the user's opinion of a product affected by the already existing ratings when they are trying to leave a rating. We have a bunch of threshold parameters which control how many stars are there in the rating that the user leaves, and we have a bias towards 5-star ratings, because a lot of users on online platforms just leave 5-star ratings irrespective of their experience. So with these parameters, these are parameters built out of hypotheses we have about the data generating process, and now we have a generative model out of this. So putting this all together, we are working on a Python package to make this accessible as well. What we can do is we have a marketplace simulator class, for instance. Sorry. And once we pass in the parameters that we want to have in the simulation, we are able to simulate data. And what that means is, on out the other side, we get actual time series of ratings. So the time series of 1, 2, 3, 4, 5 per product as the output. Um, uh, and so this with all of this, we have a generative model with interpretability built in, because we have built in something that we talked about at the start. We have a generative model where we have been able to directly specify parameters of consequence. We have been able to specify these cost parameters or these herding parameters, which really matter in this process we are studying. So I hope to have convinced you that simulation based models do fulfill that role. But the question still remains about how we can do Bayesian posterior inference in these models, because we know from the generative models that we have right now, we can generate really good data, but they are not interpretable. So we don't have both of these criteria met in any of the generative models we have. Can we achieve that for the simulation based generative models? And it turns out we can do that. That's what we did in our application case as well. But before we jump into that, I want to talk to you about why Bayesian inference is so hard for generative simulation models. And the reason for that is that when we are doing Bayesian inference, we are trying to infer a posterior over the model parameters. So we want to get the P of parameters given the data. And to do this, we need two pieces of information. We need the prior over the parameters, which is always available because that's something we specify ourselves as modelers. And we also need the likelihood, which is the P of data given parameters, which is usually defined by the model. So if you have something like a linear regression, the straight line itself defines this likelihood. But if you think about it, if you take a moment and think about it, we do not have access to this likelihood function for the generative simulations. These in our agent-based simulation, for instance, we can have a marketplace, we can bring users into the marketplace, we can simulate ratings from that marketplace, but we cannot write down this likelihood function. And that's why we need to perform likelihood-free Bayesian inference, which is much harder to do than the standard ways of doing Bayesian inference. And that is also where the title of my talk comes from. So with that, uh, we also have an additional challenge in our specific use case, that our likelihood-free inference setup needs to scale with the size of the marketplace's product catalog, which can be hundreds or even thousands um, of products. And it turns out that some really interesting research in the last couple of years in the field of probabilistic machine learning has helped with addressing this problem. So we use this method called sequential neural posterior estimation, or SNPE, which is a relatively new method published in the last 2 to 3 years. And the authors of this project have also developed a really well constructed toolbox to be able to use the algorithms that they have published about, which is another example of how well designed software is allows for accessible and open science, and allows us practitioners to apply these algorithms to our use cases. So how does SNPE work? So what it does is basically it trains a posterior estimator from the simulated data. So what it does essentially is that it trains some sort of neural network to which we input the simulated product ratings. So that goes in from one side, and on the other side we get the posterior over the parameters. But keep in mind that the output over here is a complex and high dimensional probability distribution. It's an 8-dimensional probability distribution in our case, and it's not the usual sort of output that we have in regression or classification problems. And given this is a high dimensional and complex distribution, it's not very easy to parameterize it in any form. So what SNP does is that it uses actually deep generative models, uh, specifically normalizing flows, to help in this situation. So we have the generative models that I talked about right at the start of the talk coming back here, but in a different role. So they're not generating data here, but they are inferring the posterior distributions for other more interpretable generative models, the simulation models that we talked about. So how normalizing flows work is that they begin with a simple distribution, maybe a Gaussian, which I show on the left over here, and apply repeated transformations to eventually convert that simple distribution into the complex distribution that we are trying to model, which is our 8-dimensional posterior distribution. The trick here is that each of these transformations is parameterized by a neural network, so it's trainable with training data, and that's where that's where the machine learning part in this whole process comes in. So with all of that set up, we just need to, in our specific use case, we need to add one more thing, which is that we have to input the rating time series into the SNP network. So the input in our case is time series of ratings for different products. And if you think about it, these time series do not have a fixed length. So you cannot, there is nothing in a marketplace controlling how long the rating time series for a product would be. So to be able to embed them to a fixed dimension, we use 1D CNNs. And we are able to train these 1D CNNs together with the posterior estimating normalizing flow. And so that's great about this setup, that we can use this as one big neural network and train it in one go. We evaluate the performance of the entire inference network by using predictive log likelihood on a held out set of simulations. So we input once this training procedure is done, we can input an actual time series of product ratings from a real marketplace, and we can get the 8-dimensional posterior out the other side. And so with that, we are able to use this way of doing Bayesian inference in our specific use case as well. And we have set it up in our code base as well, that once we feed in the parameters and we feed in the simulations, then we can infer the SNP posterior, and once the posterior has been inferred, we can feed in real data to get posteriors that are specific to individual products. So the real data that we use are ratings data from a UK based online retailer that we already had in hand. One of the other really great things about this setup is that the inference network needs to be trained only once on the simulated marketplace data. So we don't have to train it for every product, for each and every one of the hundreds or thousands of products that we might have. In our data set, we have about 1,400 products. We train it once, and then we can do amortized inference, as it's called, using the same trained network across the entire product catalog. And that's a great property to have. So now we have the posterior distribution over the parameters. We have a generative model that is interpretable. We have a posterior distribution over the parameters of the model. How do we use that? So we can do a lot of different things, and I'll just give you a couple of examples of what we do in our project, for instance. So we could do something like this. We could plot out the product specific 8-dimensional posterior distributions. So this is the posterior distribution of an individual product. It is 8-dimensional, but I'm showing you pair plots of pairs of parameters in this distribution. So we have the parameters on the left over here, and we can say interesting things about this product. So for this specific product, for instance, we can say that leaving a positive rating is easier than leaving a negative rating. And that we can say because if we look at the marginals of rho plus and rho minus, the first two top marginals over here, the marginal mode of rho plus is much smaller compared to the marginal mode of rho minus. So the cost to leaving a positive rating is smaller than the cost to leaving a negative rating. So these are the directly interpretable things we can say right out of the model we have built. Um, we could even go one step further into downstream predictive tasks. And this is also a standard Bayesian way of doing this, where we sample from the posterior to produce predictions, and that is called a posterior predictive distribution, sometimes also called posterior predictive checks, for instance. And what we are doing here is that we are running the simulation model using parameters sampled from the inferred posteriors. And this is functionality we have put into our code base also, that we can sample from the inferred product specific 8-dimensional posterior for each user who comes to buy and review. And we can just input the simulation parameters into the simulate method, and it is able to sample from that. And this is fundamentally different actually from how simulation models are used yeah, are usually used, because usually you fix the simulation parameters in one go and then you simulate. But here we are sampling from a probability distribution while simulating. So that's additional functionality we have put into our code base as well. And when we do that, we can do things like this. So this figure here shows the moving average rating of a particular product. And in black over here are 20 um, 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 in black over here is the moving average rating over 20 ratings from a particular product, from about 20 ratings for a particular product. And these ratings were not seen by the SNP training procedure. We trained the SNP procedure using the other ratings of this the previous ratings of this product, and then we simulated out into the future. And one example simulation is shown in red over here. So we did 32 simulations. One out of the 32 is shown in red over here. And in blue with the error bars, which is mean plus standard deviation, we have the mean plus standard deviation of the 32 simulations that we did. And we can see that these all, fall on top of each other. So the simulation model is able to reproduce the data that looks like real data. And in this rating prediction task, which is a particularly hard task, we see about a 7% improvement in RMSE across all products using the simulation model over here, compared to a baseline which has been built out of multinomial predictions from rating count histograms, which is usually what you would do. Um, so
Hi,
with all of
Narendra.
that, yeah.
Apologies for interrupting. You have about 2 minutes left in your talk. Would you like to leave some time to field some questions?
I think I'll finish this and maybe take it on Discord.
Okay, sure.
Yeah. So yeah, so I hope I have convinced you that that generative simulations can fulfill both of the criteria that we started out with. So with that, I'll end my talk and just give special thanks to the Google Cloud Academic Research Grant for computing resources for this project, and also to Tilburg Science Hub for RA support on our project. And Tilburg Science Hub is a really interesting open science collaboration here in the Netherlands. They are giving a lightning talk on Saturday, which I encourage you guys to go to if you are interested in open science and all that. And thanks a lot for your time. And I don't know if we still have time for questions, or I'll be available on Discord as well.